Hello everyone from Math 2200 Discrete Mathematics. Professor Winson here again with a video on your ZyBooks Section 1.7 titled Quantified Statements. Alright, so I'll read the opening here. We get some definitions in bold down here. Now you've already seen predicates and propositions and quantifiers. But universally and existentially quantified statements can also be constructed from logical operations, right? So we can put in disjunctions, conjunctions, implications, biconditionals, all negations, all that stuff. Consider an example in which the domain is a set of positive integers and define the following predicates. So the predicate P of x is the statement x is prime, O of x is the statement x is odd. So then we can combine predicates now with, again, these logical operations. Then the proposition, remember this backwards E symbol means there exists, or there is at least one, right? There exists in x, where x is representing some positive integer. So there exists a positive integer such that, and then you see in parentheses here the whole statement after this is true, such that x is prime and not odd, right? Negation. So there exists a positive number, a positive integer, that is prime and not odd. The proposition is true because when x is 2, right? The number 2 is both prime and not odd at the same time. And that has proven this statement, right? It's a there exists statement to prove an existential statement true, right? You only need to find one example, one value in the domain that makes it true. Some other examples here. The proposition, for every x. Remember this upside down A means for every or for all. Means every domain value, every positive integer satisfies the following statement. If the integer is prime, then the integer is odd. All right. This is an implication. Says that for every positive integer x, if x is prime, then x is odd. This is false because of 2, right? A counterexample. To show that a for every statement, a universal statement, is false, you only need to find one example where the statement doesn't hold. Because 2 is prime, so it satisfies the hypothesis. The hypothesis would be true, but the conclusion would be false. 2 is not odd. Right? So remember, when the hypothesis is true and the conclusion is false in an implication, the implication is considered false. Alright, so the universal and existential quantifiers are generically called quantifiers. So simple, right? Just when you hear the word quantifier, you're going to see this upside down A or this backwards E symbol. There exists, or for all. A logical statement that includes a universal or existential quantifier is called a quantified statement, right? So this here earlier is a quantified statement. This also is a quantified statement. The quantifiers, for all and there exists, are applied before the logical operations, right? The and, the or, the implication, the biconditional, etc. This means that the statement for all x, p of x, and q of x is equivalent to for all x, p of x, and q of x, as opposed to for all p x, and then parentheses. So if they're basically order of operations here, basically what they're saying is if there are no parentheses and you see a quantifier, you perform the statement, you look at the statement with the quantifier attached first. You would imagine parentheses around this. You do this first and then do all the other logical operations and then do the and q of x. So you see that here. Whereas opposed to over here, see the parentheses are present, so I would look at the statement in parentheses first, and then apply the quantifier to them. All right. So pay attention to where parentheses are present. All right. So some examples, a little activity here for the following questions. The domain is the set of all positive integers again. All right. The first three questions use predicates O and M, which are defined as follows. So O of x is the predicate, x is odd. M of x is the predicate, x is an integer multiple of 4. Right? So meaning 4 times 1, 4 times 2, 4 times 3, 4 times 0, 4 times -1, right? Any integer. But we're only looking at, again, the positive integers, so no negatives, no 0, just 4, 4 times 1, 4 times 2, 4 times 3, 4 times 4, etc. Alright, so we're asked to indicate whether each quantified statement is true or false. Alright, so I'll do a couple of these, there's only 4 of them. I'll do one there exists and one for every, so 1 and 3. So I'll bring this up on some paper. Make this a little bigger here, and you can see. And I'll write this out. Alright, so I've written out the first statement. Now in English, and you'll see some exercises at the end of this where you're asked to translate statements into English sentences. So this is a there exists, right? That means there is at least one. X represents a positive integer. Remember here the domain is the positive integers. And then you have, notice the parentheses, right? The parentheses around the O of x and M of x, right? They have the conjunction symbol and there. So in English, this means that there exists a positive integer called x, a positive integer say x, such that, and then the following statement, the statement after the quantifier, such that x is odd, right? O of x, and at the same time, x is an integer multiple of 4, such that x is odd and an integer multiple of 4. Right. Now the question is is this statement true or false? Remember the domain, I'll write it up here. Right. The domain is the set of positive integers. So all the values that x can be replaced by are 1, 2, 3, 4, 5, etc. Now to show that an existential statement, again, is to show that this is true, I only need to find one value in the domain that makes this true. Now let's look at some examples, and we'll see if we believe it or not. We're not in the proofwriting chapter just yet. You saw me do a couple proofs in previous videos, but they were very basic, and we're not doing proofwriting right now. Let me actually blow this up here so we can see the whole, see a little bigger. Okay. So I'm not gonna if this ends up being we're gonna just go over some examples and kind of see if we feel that it's true or feel that it's false. Again, if you find one, you've proven it's true. But to prove that it's false, you'd have to prove that it's always false, for all the values in the domain. That we're going to go into that a method for that in chapter 2. All right, but how about when x equals 1? Is 1 is O of 1 and M of 1? Is that true? Well, O is odd. 1 is odd. Sure, 1 is odd. But is 1 an integer multiple of 4? No. Right. So that's That's a false statement. I'll put F for false, T for true. When X is 2, is O of 2 and M of 2 a true statement? 2 is not odd. So remember, an AND is only true when both are true. So this is false, right? Because O of 2 is false. M of 2 is also false. X equals 3. Is O of 3 and M of 3 true? Well, 3 is odd, but 3 is not a multiple of 4, right? So this is also false. And I'll tell you right now, you could keep doing this, and it will always be false. Like I said, though, we're not gonna do a formal proof. That's formal proofs will more be saved for chapter 2. But think about it. In order for this to be true, for an integer would have to be odd and a multiple of 4. But if you're a multiple of 4, you're going to be even, right? A multiple of 4 will also be a multiple of 2, and any multiple of 2 is even. So this is basically saying that you'd be odd and even at the same time, and this cannot happen. Right? And that's kind of how, a little out loud, how we kind of go about proving it when we get to chapter 2 stuff. All right. So this is a false statement. And again, when you click on where it comes up, the explanation there. All right. Then I want to look at number 3. The for all statement. So again, I'll write it out. We have pull up some paper here for you again. So number 3, we're looking at the statement for every x, right, for all x, and then in parentheses we have m of x implies, right, implication not O of x. Remember, this is the negation symbol, and that's all in parentheses. So in English, if I was writing this is a complete sentence, and there's the domain again. The domain's all positive numbers, positive integers. This means for all positive integers, say x, right? Again, x represents now not just a single integer, but it kind of represents any positive integer. Then the following statement will be true. If x is a multiple of 4, or an integer multiple of 4, then x is not odd. And another way to say not odd when you're talking about integers would just to be say that it's even, right? Okay, so again, I'll pull this up, make this a little bigger. Now again, we can go over some examples. Now the thing is, this is a for every, right? This means that this statement needs to be true for all positive integers in order for the whole statement to be true. To prove that it's false, you just need to find one integer that makes this a false statement, right? Okay, so let's see. Now again, I'm not going to, in order to prove that it's true, we'd have to go for every integer. There's no way I could possibly write that out. So again, the more formal proofs and how to actually construct proofs, we're going to do in chapter 2. I'm just going to go over several examples right now. So again, I'll start off with this is for every positive integer. So I'll start off with 1. Then look at the statement. M of 1 implies not O of 1. Now remember implications. Right? Remember implications is you have a hypothesis and a conclusion. If this, then that. Is 1 a multiple of 4? No. So we have false implies, and then is 1 not 1 is odd. So is 1 not odd? That would be a false statement. Right? O of 1 is true. Not O of 1 would be false. But you remember when the hypothesis is false? Remember, when the hypothesis is false, the implication is a true statement. So this statement is true, for x equals 1. How about for x equals 2? So I put in 2 for x. How about m of 2? Does m of 2 imply not O of 2? So again, look at the truth values of the hypothesis and the conclusion. Is 2 a multiple of 4? No. So that's a false hypothesis. So again, this is going to be a true statement. Now 2 is not odd, that's true, but it doesn't matter, right? The hypothesis is false. And the hypothesis is false means that the implication is a true statement. Right. So far so good. It's true for 1, it's true for 2. Is it true for 3? Well, the same thing's going to happen as with 1. We have m of 3 implies not O of 3. That is also true because, again, just like for m of 1, the hypothesis is false. 3 is not a multiple of 4. Really, the only things that this is, it's going to be true for anything that's not a multiple of 4, right? If the hypothesis is false, we have a true implication, a true statement. So how about 4 multiples of 4, like 4, 8, 12? If I plug in 4, m of 4 is true, O of 4 is false, but not that would be true. You'd have true implies true all the time, right? Any multiple of 4 is going to make the hypothesis true and the conclusion true, which would make this a true statement. All right. Again, I'll just pop that over here. When x equals 4, we have m of 4 implies not O of 4. So you have, and this will happen for any multiple of 4. True implies true. And when both the hypothesis and the conclusion are true, the implication was true. So it looks like it's going to be true all the time. Again, this doesn't prove anything, right? You would have to do this forever. Like I've been saying multiple times, we're going to go over more formally proving statements that are universal in chapter 2. Right? But it does give us a rough idea. It's like, hey, I feel like, just because I've seen a couple examples, I feel like this universal statement is true. And if you think about it, it would be. Right? For any non-multiple of 4, this is true, and for any multiple of 4, the hypothesis and conclusion would be true, so the whole thing would be true. Right? Right, so back here, I'm saying this is a true statement. Right? It says you can work on 2 and 4 yourself. All right. Now some more definitions. So a variable x in the predicate p of x is called a free variable, because the variable is free to take on any value in the domain. Right? When you just have a simple predicate written by itself, just p of x or q of x or o of x, m of x, whatever, or O of xy, right? You saw predicates in previous sections with multiple variables. Those variables are called the free variables because they can take on any value of the domain. But as soon as you put a quantifier in front of a predicate, as soon as a quantifier is acting on a predicate, that predicate becomes what's called a bound variable. The variable in the predicate is a bound variable. So you see, for every x, p of x, the x is attached to a quantifier. Right? X is attached to for every. It's bound to for every because the variable is bound to a quantifier. A statement with no free variables is a proposition because the statement's truth value can be determined. All right, so be careful. All right, be careful. Pay attention to parentheses and what predicates actually have quantifiers acting on them. So in this statement, for every x, p of x, and notice that's in parentheses, and then afterwards and q of x, see the x in this predicate is bound to this quantifier. But the x in this predicate is not bound to a quantifier, right? This isn't in the set of parentheses with this p of x. So this x in the p of x, this variable, is bound. This x in the q of x is free. And they explain that here. The variable x in p of x is bound by the universal quantifier, but the variable x in q of x is not bound by that universal quantifier. Again, because of the use of parentheses. Pay attention. So this statement as a whole, right? There's a variable that's one variable that's bound, one variable that's free. So it's not a proposition, right? Only when all the variables are bound, right? When there are no free variables is it a proposition. Now, in contrast, the universal quantifier in the statement here, see how there are parentheses around the p of x and q of x this time? So this entire statement is acted on by this universal quantifier. So both these x's in here, they're both in parentheses. Both these x's on the p of x and q of x are bound to this universal quantifier. Right. So this is a proposition, since all the variables are bound. So some examples. Right. So again, I'll write some of these out. Just the first couple here. So we have the first statement. See, there exists an x such that p of x. This existential quantifier, there exists, acts on the p of x, right? This quantifier is attached to this statement, p of x. So the variable x, right, the variable x in here is bound by this existential quantifier. X is bound by the existential quantifier, right, by that. So x is a bound variable. And that's the only variable showing up in any statement here. Right? So there are no free variables. Right? There are no free variables, no unbound variables. So this statement is a proposition. Is a proposition. It is either true or it is false. You can actually determine the truth value. Right? Okay. So their statement is, the expression there exists x such that p of x is a proposition. That's true. It is a proposition. Right. And again, see the variable x is bound. All right. The next statement, where you have there exists x s such that statement s of x is true, or r of x. Now, do you notice how the parentheses are around this, right? And even if there weren't parentheses, they'd be implied to be here. Remember that order of operations I mentioned earlier. So this x in the statement s of x is bound by the there exists, right? This statement, this variable x is bound by this existential quantifier. So I'll say bound. But this x in the statement r of x, that is, the statement r of x is not in the same set of parentheses with the statement s of x. So this x is not bound to that quantifier. There is no quantifier attached to the statement r of x. This has no quantifier. It has no quantifier. So it is free. Right? That x in the statement r of x is a free variable. And since there is a free variable, there is at least one free variable. There is a free variable. Means that this statement is not a proposition. You cannot tell the truth value of it. Right. So their statement there, this expression is a proposition. No, it's not. That is false because of the free. And then you can look at the other two. All right. All right. So now we get into logical equivalence with quantified statements. And as earlier, two quantified statements, whether they expressed in English or the logical symbols, have the same logical meaning if they have the same truth value, right, regardless of the value of the predicates for the elements in the domain. All right, so just like logically equivalent statements, when we looked at those earlier in the chapter, all right, two logically equivalent statements have the same truth value no matter what. All right, so they give an example here. So here, consider an example: a domain consisting of the set of people invited to a party. Right, so the domain of the variables is, the variables can represent people, and these people that were invited to a party. And we define the predicates. The predicate P of X is the statement person X came to the party, and the predicate S of X was, person X was sick. The statement everyone was not sick is logically equivalent to, for every X, not S of X. Right? This is saying every person at the party, right? For every person at the party, this is true. They were not sick. Right? Everyone was not sick. So we can show how we can translate back and forth between English statements that are true or false English propositions and logical propositions with notation. Okay. All right. So they give some tables here and whatnot, and I'll just go into an example with the activity. All right. So for the following questions, the domain for the variable X is a group of employees working on a project. The predicate N of X says that person X is a new employee. Right, so N for new. The predicate D of X says that person X met his or her deadline, or their deadline. All right, so D for deadline. And consider the group defined in the table below. So here we have a table where the domain, right? The domain is the group of employees working on. The domain is all these four employees: happy, sleepy, grumpy, bashful. Right? Some of the seven dwarves. You don't have to think of them that way, but so here's the domain: just these four people. And then the truth value for each of the predicates. N of happy, right? And I'll write this out. Let me show you that what this table is telling us here. All right, let me shrink this down a bit. All right. So what this table is telling us, if you look down the first column, right, this is saying that N of happy, right, I replace X with the person, the employee happy, is a false statement. And what does that mean? That just means that happy is not a new employee, right? That's what predicate N was. Happy is not, I'll just say not new, not a new employee. Right? And if you look down the second column, D of, and let's say sleepy, right? Replace X with sleepy. Looking down the second column, D of sleepy is true. So all that means is that sleepy, met his deadline. Sleepy met the deadline. It is true. Okay, so hopefully you can see how to read these tables. All right. So getting rid of the paper there. So I just got a few things here. I might just do them all. All right. Is the statement every new employee met his deadline true or false? All right. True or false. Now this one you can kind of just look at the table. Every new employee met the deadline. So I look at the table and only look for the new employees, right? Because this is only a statement about the new employees. Well, so I'm not looking at happy or sleepy. They're not new. N of X is true for grumpy and bashful. They're the new employees. So every new employee is about grumpy and bashful. And did they meet their deadlines? Yes, right? Both have trues in the D of X column. So that is a true statement, right? That is a true statement. Every new employee met the deadline. Now, think about this statement. Is the statement for every X? Now remember, X is all the employees, not just the new ones. For every X, N of X and D of X. Is this statement true or false based on this table? All right, so again, I'll bring the paper back. Now the question is, for every X, N of X and the conjunction D of X. Now, if I were writing this in English, this means that every employee, right, for every employee, because X represented all four of these guys, right? Every employee satisfies the following statement. They are both new and met the deadline. So every employee is new and met the deadline. That's how I'm saying it in English. Is this a true statement? No. Because this is saying every employee is both new and met the deadline. Happy's not new. Sleepy's not new. All right, and again, you can go through the domain here and just replace, see if this statement is true for all the employees. So, if I just do, number 1 here with happy, is N of happy and D of happy, is this a true statement? Well, N of happy is false. And, D of happy is also false. This is a false statement. Remember, both have to be true for the whole thing to be true. So this statement they just gave me is false, right? Because I just showed you, here's an employee that makes this a false statement, happy. Right? To show that a universal statement is false, you just need one counterexample. Happy would be a counterexample. Sleepy as well. Right? Sleepy would also be a counterexample. So that statement is false. And again, they show the explanation there. So that means that this statement, the statement in number 1, every new employee met his deadline, and this statement in logic here, these are not logically equivalent, right? Because they do not have the same truth value. Right? How about this statement? Select the logical expression that is equivalent to the statement, every new employee met his deadline. Well, it's not this one. That's the one we just saw. So it's got to be this other one. You see, for all X, N of X implies D of X. This is for all the employees. If they are new, then they met the deadline. So this is saying that all the new employees therefore met the deadline. That's logically equivalent. It has the same meaning as every new employee met his deadline. Right. I hope that makes sense. And again, you can go through and check. We said every new employee met his deadline is a true statement. I can go through and check by plugging in all the different values from the domain, plugging in all the different employees, which again I'll do over here. All right, so we have the statement for every employee. The following statement is true. It's in parentheses. You have N of X implies D of X. All right. And I'll bring this table back up so we can see all the truth values. And then I just go one employee at a time and check. For happy, let's replace. Let's see if this statement is true for all employees. Happy, we have N of happy implies D of happy. That's a false statement implying a false statement, right? But remember, if the hypothesis is false, the statement as a whole, the implication is true. So it's true. This statement is true when it comes to happy. Then for sleepy, same thing. You have N of sleepy implies D of sleepy. This is a false hypothesis, so it doesn't matter what the conclusion. I mean, the conclusion is true. We met the deadline, but you have a false hypothesis, so the implication is a true statement. So it's true for happy. It's true for sleepy. And then is it true for grumpy? Right, so I plug in grumpy for x. Right? Is n of grumpy implies d of grumpy? True. Well, this is true implies true. A true implication. And the same thing goes for bashful. Right? Also bashful. Bashful would have the exact same thing as grumpy. True implies true. So this is true. Right? So this whole statement here is a true statement because for every employee, this statement here is true. Right? So it is logically equivalent to saying every new employee met his deadline because they're both true. They have the same truth value. All right. This is basically the same thing, but with a there exists. Right. So again, there exists. There is at least one. Right? You're just looking for one to make a statement true. So this one I'll just say out loud and not write on paper. So the domain again is the group of employees. These 4 employees here is the domain. They can replace your variables. N is the new employee one. D is his deadline. It's a different table, but the N and the D predicates mean the same thing. All right. Is the statement there is a new employee who met his deadline true or false? So again, this is only talking about it. The question is there a new employee that met the deadline? So I don't need to look at the old employees, people who aren't new. Happy and sleepy aren't new. I'm not looking for them. Look at the new employees. Grumpy did not meet it. Bashful did not meet it. So of all the new employees, none of them made the deadline. So saying that there is a new employee who met the deadline, that's a false statement. I can't find one. Right. Is the statement there exists an employee such that if they are new, then they met the deadline, true or false? This statement here is the same as this statement here. This is saying there is an employee such that if they're new, then they met the deadline. You can't find one. Right, but this is saying this is basically saying there is a new employee that met the deadline, and we just showed that was false. And again, sorry. Oops, nope. It is correct because of the happy and sleepy. I apologize. I am sorry. Yeah, I should have written it. Maybe I should have written it out. There's good advice for you. Yeah, sorry. Let me actually go through and plug in the values like I was doing earlier. All right. Sorry, this is true. I can find one that makes that statement true, and let me show you. Okay, so again, the statement here is, there is an employee that satisfies the following statement, that makes the following statement true, that N of X implies D of X. Yeah, then I'll go through the list of employees, right, and see if we can find just one, right? All we need to do is find just one that makes this statement, a true implication. And it would be true for happy. I wasn't focusing. I'm sorry. Right? If I go, if I plug in happy for X, N of happy implies D of happy. This is a false hypothesis. False conclusion. It doesn't matter though. The hypothesis is false, so this statement is true. So this is a true statement. Because again, all I need to do is find one. Is there a single employee? Is there at least one employee that makes this a true statement? and that would be happy. Sleepy would also make it true, but as long as you find one. All right, so that was a true statement. My apologies. So that means that this is not logically equivalent to this. I misthought. I'm sorry. Because this is false. This is true, and the statement "there is a new employee who met the deadline" is false. So then this last one, we just showed that there is a new employee who met the deadline is not logically equivalent to this one. So it's got to be logically equivalent to there is an employee that is both new and met the deadline. Yeah, this is what we wanted. Right? We couldn't find one. We couldn't find one that was both new and met the deadline, right? So this one would be false, just like the original statement. Okay. Yeah, and if you don't believe it, take this statement here, plug in all the different values. Plug in happy, plug in sleepy, plug in grumpy, plug in bashful, and you won't be able to find any of them that make this true. So this would be a false statement, just like the original one, therefore logically equivalent. All right. Translating, you can read this example. I've been kind of translating here a little bit, right? Where you translate English sentences into logically equivalent statements in logic, right? And they have little videos here even, so I'm not going to watch videos within my video. You can do that on your own. Alright, so let's do this here. I'll just pop in a couple. In the following question, the domain is the set of 4th graders at Lee Elementary School, right? So all the 4th graders, whoever they are, is the domain. The predicates P and Q are defined as follows. P of X is the statement, the kid took the math test. Q of X is the 4th grader is present today. All right, so let's read these. All right, and I'll just go a couple of them. For all X, that means for every 4th grader at this school, if they were present, then they took the test. So this is for every 4th grader, if they were present, then they took the test. So every student who is present took the test. That's the third one, right? So hopefully that makes sense, right? It's like for every student at the school, every 4th grader, if they were present, then they took the test. So everyone who was present took the test. Okay. This one. There's at least one 4th grader at this school such that the following is true. There's at least one 4th grader at the school such that they were present and did not take the test, right? That's the negation. So there's a student at the school, there is a 4th grader that was there, but at the same time did not take the test. So there is a student who was present and did not take the math test. That would be this last one here. And you could do the rest, hopefully. There's not that many. Alright. And then just like now again we're doing challenge activity here. There are 8 of these. All right, I'll just do the first few of them maybe. So I start, and all you're asked to do is determine if it's true or false. Now again, don't guess, because every time you get it wrong, it's just going to make you do another one. All right. So we're our domain here. Our domain is Ann, Bob, Joe, right? Just these 3 people. And we have 4 predicates, A of X, B of X, C of X, D of X, and then the truth values, for each of these inputs, for each of Ann, Bob, and Joe. We're given the statement, there exists an X. So at least one of these, Ann, Bob, and Joe, satisfy the statement A of X and D of X, make A of X and D of X true. All right, so let me show you some paper. So it says, there exists an X, there exists a person in this group, such that predicate A of X becomes a true statement, and D of X, right? We're trying to see, is this true for 1? I just need to find one value, one person that makes this true. Now you could go through each one, if you see it already, great. If not, just go through them one at a time. How about when x is an? Is A of an and D of an true? Well, A of an is false, so no. That's false, so she's not satisfying it. How about for Bob? Is A of Bob and D of Bob a true statement? Well, A of Bob is true, and D of Bob is also true. So this is true, and there we go, Bob. Bob makes this a true statement, right? Because it's saying there is a person that satisfies this condition, right? That satisfies this statement. We just found it. It's Bob. So the statement is true. And it says now, let me get rid of the paper. It says now select an example, right? A row in the table that shows the Bob. Bob was the example, right? And move on. All right. So here again, there exists. There is at least one. Right? So again, you only need to find one. And if you can't find one, then it's a false statement. There is a person such that B of x is true, or, remember this is or, A of x is true, or both. So there's at least one person that makes this whole statement true. Let's see. How about an? Now this time I'll just say it out loud. What's B of an? False. What's A of an? False. So false or false is false. And doesn't make this true. We have to move on to Bob. B of Bob is false. A of Bob is also false. False or false is a false disjunction. So Bob doesn't make this true, so we have to move on to Joe. And again, you have false or false. This is a false statement, right? They're saying there is a person that makes this statement true, but we couldn't find one. So it's a false statement. Great. All right, now we have a for every. All right. So in order for this to be true, every single person, and Bob and Joe, need to make this true. C of x and A of x. Alright, so let's check an. C of an is true, A of an is true, true and true is true. So an works great. But it's got to work for all. Right? So let's do Bob. C of Bob is false. A of Bob is true. False and true is a false statement. So Bob would be a counter example, right? This is saying for every person this is true, but Bob makes it false. So false, and what's the counter example? Bob. Okay. So I think that's enough. I think hopefully you get the gist of what's going on there. I did a couple existentials and one universal. All right. And then you have your additional exercises, which again you can see the solutions to if you want to practice. Some of these will be in assignment 2 that I've posted this week in your week 2 module. Those are the ones you're going to write out and hand in and submit via Canvas. Not all of them are assigned. Right? I didn't assign everything. So I would recommend even going through also the ones I didn't assign as well, right? Just to get more practice and check the solution. And don't look at the solutions right away. Please try to do these things before you look at the solutions, right? You're not going to learn anything if you just look at and copy solutions, all right? And if you don't learn anything, if you just copy solutions down, when I give you exams later, you're going to have a real tough time. All right, so that was it for section 1.7 on quantified statements, and thank you very much for watching.